Now let's look at how do we implement Nelson-Oppen in a practical situation. So enumerating all the equivalence relation over shared variables is very expensive. The goal is to minimize the search. Okay, so you don't want to enumerate all of them. You want to enumerate as few as possible to find if there is a satisfying assignment or not. So first is that decrease the size of S. You just try to make sure that least number of common variables are found, and if two of them are equal, they're replaced very as soon as possible. The second is that you want to find efficient strategy. Incremental strategy you build as incrementally, and something goes wrong, you backtrack or something like that. Not enumerating each one of them explicitly. So how the efficient search possibly can work? It's a deep like search. You make decision. Okay, so you can introduce equality between already existing equivalence classes. You say, okay, now these two are same, or you can introduce this equality. You make a decision that so far you have built your equivalence class up to some point, and then you increase an equality or introduce a disequality between equivalence classes. If you make this decision wrong and some one of those theories become unsatisfiable, you backtrack, undo your decision, and move on to making another decision. Third thing is a propagation, and that's what we have seen is very important aspect. If already you build up to some point equivalence relation, and then what does it imply? Does it imply new equalities to be derived from the current situation? Or you can also derive disequalities, so that you propagate this further using deep like structure. You can basically explore all possible equivalence relations in an incremental fashion. However, there is a particular situation when theories are convex. This method is very efficient. You really don't need any decisions. Everything is done by propagations, and we will see what is that convex condition. What is the convexity condition? If you have a formula F in a given theory, and it implies that there's some bunch of equalities, let's say n equalities, that means there is exactly one of them that is implied by F. Okay? This is called convexity property. So not all theories are convex. For example, theory of integers is not convex. However, theory of rationals is convex. Here's an example. This formula says x is between 1 and 2, y is 1, or z is equals to 2. So that means y is equal to x or z equals to x. Right? So there is a disjunction here. From the above, we can conclude that LHS implies any of the equality in the right hand side. So let F be a conjunctive inverse formula, and let S be a set of variables that are common between variables, between sub-formulas, and then let's say it's initially empty. If F is empty, return satisfiable. If F is not empty, you can pick a literal L, which is, let's say, belongs to ith theory. Then you take this literal out of the set F and simplify L to L prime, add the fresh symbol names for the alien terms to S, and add L prime into your Fi. That's a standard purification process. If Fi is unsatisfiable, then return unsatisfiable. If that is not the case, then for each term or variable S and T occurring in S, check if Fi implies T equals to S or T is not equals to S. If you discover any of those new facts, add it to other Fj's, because Fi implies this thing, then everybody else should know that this equality or disequality always holds. Go to step 1 and keep doing it. Okay. If theories were convex, then the above well-calculated answer. Otherwise, we need to explore the far reduced space of equivalence classes in the case of satisfiability response. So let's look at a few examples to understand that why this method works. Okay, so let's suppose you have this formula. It has equality reasoning and it is arithmetic reasoning. Let's separate them. If we separate them, we find these two formulas. Basically, f of x is replaced by a new symbol, f of y is replaced by a new symbol, and then you say the subtraction is done in a arithmetic word, you get a value, and then w is written here. So you are at the end, you find this formula and this formula. This is an equality, this formula is equal in arithmetic. So the common symbols are these 6 variables. So what happens is, since both the theories have convexity, so we don't need to really make a decision. It is basically propagating equality from one theory to another. So you can see that this thing says that x equals to y. Why? Because x less than or equal to we already have. If you just add these two inequalities, you will find the z will cancel, y will less than or equal to x. So that means y is equals to x. If y is equals to x, if you push this equality in this world, then say okay, y is equal to x. That means u and v are equal. So you got u and v. Once you discover this thing in theory of equality, you got to tell this to the theory of rationals. If you do that, then you get w equals to z. Why that is the case? Once say u equals to v, it becomes w equals to 0. Okay, and we already knew y equals to x, right? So y equals to x is there, then y minus x, right? So it becomes 0. So z is less than or equal to 0. Okay, so if z is less than or equal to 0 and z is greater than or equal to 0, therefore z is 0. Okay, so you get z equal to 0. That means z is equals to w. That's what we discovered. Okay, now when we tell this to our equality, w and z are equal, then this is unsatisfiable. Okay? So therefore the formula is unsatisfying. Now look at the situation when theory is non-convex, and let's suppose all this arithmetic is in integers. Then what will happen? When we separate them out, remember that integer constants are also part of integer theory. They are not part of the equality theory. So you need to give them a symbol, right? So you say y equals to 1 and z equals to 2 and put them here. Okay. Now x can be between 1 and 2, right? So therefore, if we try to propagate equalities, you'll realize f z implies x equals to y or x is equal to z. Now this is disjunctive. If it was a convex theory, then it means we had have known that one of them must be true, but that is not the case here. Therefore, before passing on to E, we need to do the case split. So there's a case x equal to 1. You can see if you do x equal to y, then this becomes unsat, therefore you can get a false. And there will be another case x is equal to z, and fen x equal to z is false, therefore the whole formula is unsatisfied. Okay, so we have been looking at examples and they were unsatisfiable. That's not very good. So let's look at a satisfiable example to convince ourselves that this method actually is useful. Right? So again we have formula, we have separated these two parts, okay, fe and fz, and they have common symbol x, y, z, w. Now x can be between 1 and 3. Okay, it takes one value 1, 2 or 3, and there are three symbols y, z and w. They themselves equals to 1, 2 or 3. The x can be either equal to y or z or w, right? So that's what you're going to learn first. Okay, so I'm going to learn that x can be equal to any of the three guys. Now we have three case splits. Okay, so before that there is another issue that from this we can also learn that there is distinctness. Basically y, z and w are not equal to each other, right? So we know that they are not equal to each other. There are four variables, right? We know that these three guys are not equal to each other. Okay, and there's an x guy, right? You don't know it is equal to this guy, or this guy, right? And that is what this guy is saying. So overall, you look at your equivalence relation you're looking for has only three possible choices. Either this is true, or this is true, or this is true. Nothing else is possible. Okay. So if we add this into our constraints, x is equal to y and the distinct y equal to z, and then we'll find that x is equal to y makes this unsat. So we got unsat. And then now this x is equal to w, this stick to x, y, z, x is equal to w, that this, and then get unsat. Now let's try the third case. X is equal to z, this stick to y, z, w. Now what has an x equal to z is not a problem. Okay, this is why I allow x equal to z. So you are going to pass through, and therefore we can say it's satisfiable now, because your equivalence class is complete, because you're saying x and z belongs to one equivalence class, and then you have other equivalence class y and another equivalence class z, and they are not equal to each other. So yeah, that's, you cannot make more things equal or disequal anymore. Therefore this is complete. So now since we have that situation, we have satisfiability.